So we're looking at the interference term in the irradiance of two electromagnetic waves that are impinging upon a screen. And so this term right here, this irradiance or this interference term, we'll call it I sub 1, 2, which is this right here. Now, to really try to develop some insight, it's helpful to simplify the problem a little bit. And so one of the things we're going to do is to have both of the electromagnetic waves have the same frequency and wavelength. In other words, we're going to have monochromatic light. And so with that, we can simplify the equation a little bit down to this term right here. Now, one thing to note, this term right here, the time average of that ends up going to 0, whereas this term right here has no time dependence whatsoever, and so the time average of that is just whatever's inside that term right there. Now, cosine k s 2 minus, that's supposed to be an s1. And so we get a much simpler equation, and we can start to pull this apart. The first thing to notice is this term right here, S2 minus S1. We're going to refer to that as the path length difference. It's the difference in the paths traveled by the two different light rays. And it's kind of useful to take a look at what this means. And so if we write out this term right here, k times S2 minus S1. Well, k we know is 2 pi over lambda. And so we just rewrite this a little bit. This right here is essentially telling me what that path length difference is in measurements of the wavelength. And so we know that associated with each wavelength is a phase shift of 2 pi. And so this is essentially then telling me the phase difference between the two waves as a result of them having traveled different paths. And so I can then define a phase difference delta, which is just this k times S2 minus S1. And so from that, we get that my interference term is this thing right here. And it just depends on the cosine of the phase difference that results from the two waves traveling along different paths. And so when we go ahead and plug that back into my original irradiance, this is what we get. Just a couple of things to notice from this equation. First, if these two waves are polarized perpendicular to one another, there's no interference. In other words, we get an irradiance that's simply the irradiance of the individual light beams, as if there was no interference at all. The other thing is we get maximum interference if the two light waves are parallel to one another, if they're polarized along the same direction, in which case my irradiance is simply the individual irradiances plus this interference term. Now this occurs when delta is some integral number of 2 pi. In other words, the path length difference is just some integer number. And that's when we get this result right here. However, I do get a minimum irradiance when my phase difference is some half integer number of 2 pi, in which case we get the two irradiances minus this interference term.